Today we're going to finish acid and bases, and the new syllabus came yesterday. There wasn't. I went through the syllabus for all of biology, chemistry, and physics, and I found that there wasn't any change in the syllabus. There was only some new additions in physics, and in kinematics, specifically kinematics. Uh, there was some kind of new addition of something called motion. I don't remember what kind, but I found it was new. So there was only additions in physics and nothing else. So today we're going to start with acid and bases. In this chapter, I know this is an easy chapter, so we'll finish this fast. Let's start with the acids first, the properties of acids. Acids, we know, have a pH of below 7, and they have a sour taste and are corrosive. In acidic conditions, blue litmus paper turns red and methyl orange indicator turns red as well. So remember that when you have an acid, the indicator would usually turn red. But when you have a base, the indicator usually turns blue. You have to memorize the different colors. This is at the end of the class, but yeah. Acids are substances that can neutralize a base, forming salt and water. So acid plus base gives you salt and water. When acids react, they will lose electrons to form positively charged hydrogen ions. The presence of H plus ions is what makes a solution acidic. So an acid is an H plus donor, so it would donate H plus ions. So when you have a water, for example, when water is acting as an acid, what you will get is OH minus ion, because water here is acting as an acid, so it would donate one of its hydrogen atoms. So it becomes OH minus. And similarly, if water was to act as a base, then water would accept this proton, this hydrogen ion, and it would become H3O plus, because if it's acting as a base, then it would accept H plus ions, because remember, bases are proton acceptors. Uh, so uh, Acids with bases, remember, metal oxides and metal hydroxides can act as bases. And non-metals, remember, non-metal oxides act as acids. So acid plus base gives you salt and water. And these are some famous acids you have to know: hydrochloric acid, sulfuric acid, and nitric acid. All of them are strong acids. And so you don't have to know this. What you do have to know the reaction of acids with metal carbonates. So remember that an acid, right? An acid, for example, HCl, will react with a metal carbonate. Metal carbonates can be anything. For example, CaCO3, this is a metal carbonate. So a metal carbonate with an acid would give you a salt of that carbonate plus carbon dioxide plus water. Now, these two are the byproducts. So carbon dioxide and water are the extras, and the main product is the salt that is formed. Yeah, so you have to memorize this as well. You have to know the general rules, not very specific reactions. This was acids, and now moving on to bases. Bases have a pH value of more than 7. And a strong base would be something of around 10 to 13 pH. A base which is water soluble is referred to as an alkali. So when a base is soluble in water, it's called an alkali. And a base would usually turn red litmus paper blue. And the orange indicator, methyl orange indicator, would turn yellow. So in red litmus paper, you'll turn it blue when you have a base. But when it's an acid, the litmus paper would turn red. And bases are substances which can neutralize an acid, forming salt and water. And yeah, so this is the revision. Bases are usually oxides or hydroxides of metal. I told you metals, oxides are uh, basic. Non-metals, non-metal oxides are acidic. So when an alkali reacts, they gain electrons to form negative hydroxide ions. The presence of the hydroxide ion is what makes the aqueous solution an alkali. So, for example, sodium hydroxide would dissociate into Na plus ions and hydroxide ions. The reason that sodium hydroxide is basic is because it has the OH minus ions when it dissolves in water. So yeah, the basicity is because of this OH minus ion. And similarly, the acidity is because of H plus ions. The more H plus ions you have, the more acidic the solution would become. So the pH scale is also very important because they've specifically mentioned in the syllabus about pH and pH changes. So the pH scale is a numerical scale which is used to show how acidic or alkali a solution is. It goes from 1 to 14, where 1 is the most acidic and 14 is the most basic. And all acids have pH value of below 7. So something which is an acid, right, which is an acid would range from 6 to 0, 6 to 1, not 0. You can ignore the 0. And something which is a base, right, something which is a base would go from 8 to 14, where 8 is very slightly alkali, and 6 is also slightly acidic. So if you had a pH of 8, water, if something had a pH of 8 water, you could drink that water and nothing would happen because this is slightly acidic, slightly alkali, sorry. And similarly, slightly acidic, if you would drink slightly acidic water, that would not cause anything because it's slightly acidic. It has very low concentration of H plus ions. Remember this, that H plus ions at pH 6 is very low, whereas at 1, uh, at pH 1, the H plus ion concentration is very high. Similarly, for OH minus ions, it's very low at pH 8, and at pH 14, it's very high. Yeah, so this is basic stuff. The lower the pH, the more acidic the solution gets. This is also very basic. So if you had pH 1, it would be the most acidic. And similarly, if the higher the pH goes, the more alkali the solution will go. So if you go from 8 to 10 or 12, then it would become more acidic, more alkali. And a solution of pH 7, such as water, is described as being neutral. So it would have equal amounts of H plus and OH minus ions. And remember that on the pH scale, the blue or something which is becoming blue or purple is usually basic, whereas something going from green to red or yellow, when you become red, then you will have acidic solution. Yeah. uh, what is the importance of pH and soil acidity? So the soil pH is analyzed to indicate the acidity or alkaline of a soil. If some soil is too acidic, then it would not be suitable for plants to grow. So most plants favor a pH value of between 5 and 8. So if a pH of 3 or 1, if it was 1 to 3, then this soil would not be able to grow any plants. So the ideal pH of soil to grow plants is 5 to 8. And changes in soil which cause a pH to be outside this range will affect the plant process, resulting in reduced growth and crop yield. So as I said, if it's less than 5 and 8, 5 to 8, then you'll have reduced growth or no growth at all. So soils may become acidic from acid rain, and or it could be because of using too much fertilizers, which contain ammonium salts, or by excess breakdown organic matter by bacteria. So remember that fertilizers that are used in in soils have the ammonium ion. It has the ammonium salt. So because of this ion, this is acidic. Remember, ammonia is a base, and uh, NH4 plus, when this base gains a proton, it becomes NH4 plus. And this plus is because the hydrogen is donating its electron to the nitrogen. So when you have an ammonium ion, this is called an acid. And remember, I'll go to something called conjugate base and acid. But for now, know that NH3 is the conjugate base for ammonium ion. And similarly, ammonium ion is the conjugate acid. Conjugate acid. What does conjugate mean? When an acid gains, it loses an electron, it loses a proton, it would become a base plus the salt that you get, right? So remember that the acid here, when an acid-base reaction is happening, the acid acts as a conjugate base. Acid, when it becomes the base, this acid, right? For example, water, when it becomes H3O plus, in this case, water H3O plus right here is the conjugate acid. And because why is it conjugate acid? Because it has an extra H plus ion that it can donate back to the water. So when a species gets a proton, when it gets a proton, it becomes an conjugate acid. And similarly, this water right here has one less proton compared to this right here on the product side. So this, when a species has one less proton, it is said to be a conjugate base. And conjugate bases can accept protons to become conjugate acids. So yeah. So the addition process must be, you don't have to know this stuff. What you need to know is all of this right here and fertilizers. And remember that limestone is calcium carbonate. It can act as a buffer to neutralize the acidity of the soil. So buffers, right? I'll get to what buffers are. But for now, the basic stuff for buffer is that a buffer neutralizes the the uh, the environment. So buffers can be used in solutions. It can be used in soils. Generally, if you want to neutralize some environment, you'll use buffers. And calcium carbonate, right? Calcium carbonate. The buffers for soil is calcium carbonate right here, calcium carbonate, or calcium oxide, or calcium hydroxide. You have to memorize the three buffers for soils. So calcium hydroxide, calcium carbonate, and calcium oxide, they all can act as buffers and neutralize the environment. So the soil becomes less acidic. Right. So yeah, this was basic stuff. Now you go into the more detailed stuff. So I want to zoom in right here. So in the questions, I've not really seen this topic, but you have to know this if it comes. So pH is the measure of H plus ions in a solution. So how much H plus ions you have in a solution is determined by the pH. So the formula for finding the pH, remember, is negative log into 10, this small 10, into H plus ions, into the concentration of H plus ions. So you don't have to actually memorize this formula. I've not seen a question where they can ask you this, but what I did was I memorized the values. So basically, what I did was I memorized what negative log 10 into 1 was 1, 2, 3. So like all of these whole numbers. I memorized these, and they came a lot in handy. So what you can do is you can memorize the whole numbers, negative log 10, and the value of whole numbers till 10, 1, 2, 3, 4, 5, all of that till 10. Uh, this would be really helpful for you because you don't know how to calculate the value for log, and log calculations are very difficult. So yeah, memorize the values. And similarly, how to find H plus ions concentration. The formula for H plus concentration is 10 raised to power negative of your pH value. So similarly, like I memorized the values of whole numbers, I also memorized what 10 raised to power negative 1, 2, 3. So like till 10, I memorized them. So because why did I do this? Because remember, pH are whole numbers. So pH would range from 1 to 14. So what they'll usually do is they'll give you the values from 1 to 10 or 1 to 30. So memorize the whole numbers, the value of 10 raised to power negative to the whole numbers. So this will also come a lot in handy. So this topic is not really discussed in the syllabus because uh, this has a lot of calculations and they don't expect you to know a lot of calculations. Yeah. So also along with knowing the whole numbers, you should also memorize the value for negative log 10 raised to power 0 0.1, 0 0.01, and 0.001. So all these decimals, you should learn these three values as well. Yeah. So these are the most famous H plus concentrations they can give. So this right here, as well as the whole number values, you should memorize for the negative log function. For H plus concentration, you can only memorize the whole numbers 1 till 13, 1 till 10 or 1 till 13. Yeah. So this is how you calculate the H plus concentration. This is how you calculate the pH concentration. So yeah, this is A-level stuff. It's not in your syllabus. Yeah, so I want to focus on buffers. So what is a buffer? A buffer resists changes to pH. A buffer keeps the pH constant. So the job of buffers is to make the pH remain constant. So for example, if there was soil and I added some buffer to this soil, for example, calcium hydroxide or calcium carbonate, if I added calcium carbonate to soil, and if there was acid rain in this soil, the pH would not decrease. So this soil would not become acidic because I have a buffer in my soil. So buffers resist changes to pH. Buffer keeps the pH constant. And when you add small amounts of acid or alkali. So remember that buffers usually are small, slightly acidic or alkali or basic. This buffers cannot be strong. It can't be what am I writing? It can't be strong acids or bases. Why is that? Because if I added a very strong base to this soil, because now the soil is acidic, I have acid rain, my soil becomes very acidic. So when I add small base to this to this soil, the pH would neutralize and become to 8. So the pH would increase when I add my base. But this base is very slightly basic. It's not highly basic, because if it was very highly basic, the soil would become very basic. So the pH of the soil, it would become from 8 to 13 or 14, which we don't want. So for buffers we use very slightly weak or uh, acid or base. And remember that if you want to use strong acids, you can only use small amounts, because you don't want the pH to drastically increase or decrease. So yeah, so buffers react with the H plus ions for acids, and it would react with the OH minus ions for bases. For example, calcium carbonate is an base, and so it would react with the H plus ions in the soil to neutralize it. So that the pH would become 8. So the buffer, if a buffer is a base, it would react with the H plus ions. If a buffer is an acid, it would react with the OH minus ions. Yeah. And yeah, so why does strong acids not work? Yeah, I explained this as well. So these are the formulas. So I want to focus on one formula right here. You don't have to memorize all of these formulas, but I want to focus on Ka. So Ka, there is two very famous symbols. It's called the Ka or the Kc. And remember that Ka is right here, Ka. So this Ka, the equation is the amount of H plus ions in the solution into the amount or the concentration of base into the acid concentration. And you don't have to memorize this Ka. You only need to know this equation. And similarly, Kc is the salt, the H plus ions into the salt into the acid. And remember, Kc is the product concentration over the reactant concentration. And usually when you have, so when you're reacting an acid with a base, right, what you're getting is salt plus H plus ions or OH minus ions, right? So the products here, the products is my H plus concentration or my OH minus concentration into my salt concentration over my reactant concentration. In this case, my reactant can be an acid or a base. So Kcs are for acids or bases, and the reactants, the lower side would always be an acid concentration or a base concentration. Yeah, and remember that in Kcs, you will consider the coefficients. So if I had HCl reacting with NaOH, and I made the salt, which is NaCl, plus water, how do I balance this? I have one Na, I have two H. So this is balanced. Shit. So let's say that I have two for the sake of this argument. Let's say I had two as the coefficient. So when I have two, I will raise this acid concentration to the power of 2. Similarly, if I had this salt, if this was 3, then the salt concentration in this case right here, the salt would be raised to the power of 3 as well. So in Kcs, remember, Kcs and Ka, you will consider the coefficients. Right. So yeah, this, I think there is nothing else. Yeah. So this is a question. If you can understand this question, you've basically understood this entire topic. So yeah, solve this question. All right. So we don't have any answers, so I'll solve it myself. So consider the ionic equation in this aqueous ion solution, you have CH3O minus ions, water, and what you're forming is this CH3O minus is gaining a proton, and it becomes this right here, and water is losing a proton, and because it's losing a proton, it becomes OH minus ions. So which statement about this reaction is right? So remember that when something loses a proton, it becomes a base. So in this case, water is acting as a base, because my bad, water here is acting as an acid, because it's giving one proton to this right here. And similarly, because CH3O minus is accepting a proton, you can see it accepted one hydrogen ion, it's acting as a base right here. Similarly, I told you bases have conjugate acids. So the conjugate acid is this. This is the conjugate acid. And because water is acting as an acid here, this would be the conjugate base. All right. So what are my options? Someone said A. Water is acting as a Bronsted-Lowry acid. Bronsted-Lowry base. Water is acting as a Bronsted-Lowry base. Water right here, you can see it lost one proton. It donated one proton to this right here. So water is acting as an acid in this case, not a base. Water is acting as a base acid in this case because it's donating one proton to my CH3O minus, because you can see CH3O minus gained one proton. So yeah, this is wrong. A is wrong. So B says that CH3O minus is a Lewis acid. CH3O minus, you can see, I told you it's a base. So this is wrong as well because it is gaining one proton. If something is gaining a proton, if it's gaining proton, then it's called a base. If something loses or donates protons, then it's acting as an acid. So B is also wrong. The final mixture of solution would have a pH below 7. I have OH minus ions right here in my final mixture of this solution. And OH minus ions mean that the final solution would be very basic. So the final solution would have a pH lower than 7. No, it would be more than 7. So C is wrong as well. Similarly, CH3O is the conjugate acid of CH3O minus ion. CH3OH is the conjugate acid. CH3OH is the conjugate acid of my base, which is this right here. Yeah, this is right, because if it's acting as a base, then the product would be my conjugate acid. So yeah, this is right. D is the answer. And we can look at E as well. So E is saying the hydroxide ion is the conjugate acid of the water. The hydroxide ion is the conjugate base of the water, not the conjugate acid. So E is wrong as well. So the answer is D. Is this clear? All right. So see you tomorrow. So the only thing left for chemistry is organic. We finished inorganic chemistry, so physical chemistry is over now, and from next week we'll finish organic chemistry as well, and with this we'll finish the syllabus. So I'll only solve organic chemistry for the A2 syllabus, because for the AS, right? For the AS, the first year A-level chemistry, you have to know the video is on my YouTube channel. So all of AS organic chemistry is on my YouTube channel. You can see that out. I'll only solve for A2 organic A2. So for the IMAT, you have to know both because they've included alcohols, which is in AS, and they've also included what do you call that? Aldehydes. and that's in A2. Aldehydes are in A2. So you have to know both AS and A2 organic for the exam. What is the difference between Bronsted-Lowry and Lewis? Bronsted-Lowry. Bronsted-Lowry and Lewis. I don't know. I don't think this is important. Yeah, you can see that on Google. I don't know the answer. I'm sorry. Bye.